In this video, we're going to introduce ourselves to the study of chemical kinetics, which is studying chemical reaction rates. And by chemical reaction rates, all we essentially mean is the speed at which a chemical reaction is occurring. And that just means essentially how fast or how slow it's going. So when you're studying the rate of a reaction, you need a certain unit to study it. And the unit we use for a reaction rate is going to be moles per liters seconds. And that's because when we study reaction rates, we usually take a look at how the concentration is changing over time. So concentration could be represented by those square brackets there. And then the time part is the S there, that's the seconds. That could also be minutes as well, but usually concentration is going to be in moles per liter, and then the time is going to be in seconds. What you can do is you can grab the data you collect about how fast a reaction is occurring. You can see the change in concentration over time and put it on a graph. And when you put it on a graph, as we already said, the graph that you're going to analyze is a concentration versus time graph, where concentration is going to be in moles per liter and time is usually going to be in seconds. So when you're trying to study the chemical reaction rates, how fast a reaction is going, you can monitor it in two main ways, I should say. You can take a look at the rate of reactant consumption. So what that means is that how fast are the reactants being used up? Because as you know, reactant is being used up to convert to product. So you can see how fast is that reactant level going down. Or you could also take a look at the rate of product formation or product production. So how fast are the products or product being formed? So if you analyze this graph here, you can see we have time on the x-axis and we have concentration in moles per liter on the y-axis. The reaction progresses as time increases, right, from 0 to 400 seconds. And you can take a look at the change in concentration of the various substances that are taking part in the reaction, as you can see over here. This is a reaction over here, represented in the graph below over here. And so you can see that the NO2 is a reactant, so it makes sense that the curve is going down because it is being consumed or used up. Whereas the NO and the O2 are products, so it makes sense that their curves are going up because they are being produced. And so what you can essentially do is some math with this graph here to calculate what the rate is going to be. Before we do that, I just want to point out a couple things. Let's just focus on the NO2 for a second. You'll notice, we can do the NO2 and then we can do the reactants after. The NO2s are reactants, and these are products over here. So for the NO2, you'll notice that the rate of decrease is pretty quick at the beginning and then steadily starts to slow until it sort of eventually levels off. So essentially you have a very, very high rate of reaction at the beginning, or consumption at the beginning. And then production, you'll notice that the rate of production is very fast at first as well, and then eventually starts to slow down. And so that's typical of any reaction graph you're going to see, is that the rate is going to start off being the highest at the beginning, and then it'll eventually level off and slow down. And that's because at the beginning you have a lot of reactant to work with, and then over time you use up more of the reactant, so you just don't have as much there, and your rate's going to be a little bit slower since there's less there. And you're going to notice that essentially with most graphs you see. So just try to pay attention to that little detail as you see more examples of graphs as we go forward. So again, this was a graph of concentration versus time, and you can use this graph of concentration versus time to monitor reaction rates. There's actually two ways you can calculate reaction rates, or there's two types of reaction rates you can calculate. There's what's called the average reaction rate, and there's also what's called the instantaneous reaction rate. The average reaction rate happens over a period of time, a time interval. So between two different times, so between time 1 and time 2, for example. And to calculate that rate, what you would do is you would do the slope of the secant that forms between those two times that you're interested in the reaction. So for example, if we scroll down over here we have there's no specific reaction shown here. It's just for a generic reaction. We have the concentration again on the y-axis. We have the time on the x-axis. And we want to know what the average reaction rate is between 20 and 100 seconds. And so what you're going to do is you're essentially just going to choose those 2 points there on the curve, and you're going to calculate the slope of the line that forms between those 2 points. So essentially you can use those 2 points there as your values for your reaction rate. So for example, if I want to calculate the reaction rate over here, it's just like doing the regular slope. We're going to have our 2 points. Here's our T2, here's our T1. I'm going to write those 2 points down. So the second point, or well, let's start with the first point. The first point is 20, and then we're at about, so this is 0.4 here, 0.5 there, maybe about 0.41, something like that. So 20 and 0.41. So at 20 seconds, the concentration is at 0.41 moles per liter. And then our second point at 100 seconds, our concentration is about 0.10 moles per liter. So what we can do is we can simply do our slope, which is going to be our y2, which is 0.10, minus our 0.41, because that's our y1. And we're going to do that divided by our x values. So x2 was 100 minus 20 over here. And if you plug that into your calculator, well, let's actually do the math here. So we have 0.1 minus 0.41. That gives us about negative 0.31. And then we do divided by 80. And just to keep in mind, remember this was a concentration value at the top here. This was moles per liter, and this was 80 seconds. And so you're going to see where our units come from here. So we're going to do 0.31 divided by 80, and we'll get about negative 0.00. And I'm going to keep it to 1 sig fig. So I get 3875 there, which is approximately negative 0.004 moles per liters second. Now, you won't really have a negative rate. The reason there's a negative value there is because we're probably looking at a reactant being used up. Reactants will drop. So in reality, when you rewrite this, you're going to write it as a positive value, an absolute value, which means you take off the negative sign there. So the rate, the average rate between these 2 points here is about 0.004 moles per liters second. Some people also write this unit here as like the big M from molarity per second. You can do that as well. Sometimes you'll also see this written instead as moles and then liters -1 and second -1 to show that they're both on the denominator portion of the unit. That's another way you might see it written as well, but it all means the same thing. So that there was the calculation of the average rate between the two times. So there's a time interval. That's what's important to understand. Now, we're going to go take a look at another type of calculation you can do for rate of reaction. That's called the instantaneous reaction rate. This is a bit different. It's the rate of the reaction, the speed of the reaction at a particular point in time. So at a specific time, not a time interval, but literally at a specific time. So I might say at 20 seconds or at 100 seconds. And it's calculated a little bit differently. It's still a slope, but instead it's the slope of the tangent at that particular point that you're interested in. So what is a tangent? Let's go and take a look at an example in the image below. Suppose you were interested in the instantaneous rate of reaction at 20 seconds specifically. You would find that point on your curve, which is over here, and you would want to draw a tangent to it. A tangent is a straight line that goes through that point, but not through the curve, through the point. It just touches the curve at that point just once, and that's a bad drawing of it. My stylus is not very steady there. It just touches the curve at that specific point that you're interested in, and essentially nowhere else. It doesn't go through the curve. And what you've done there is you've drawn the tangent. And then same thing here. Let's say I was interested in the instantaneous reaction rate at 100. So I'd find, the point on the curve there. I draw the tangent as accurately as possible, so it only touches that point on the curve. It's nice to have a fine point pencil there so that you're only touching one place in the curve. And then you'd find the slope of that line you just drew. That's the tangent. So you might choose 2 points on that tangent there, and then do the same sort of process that you did over here, just with the tangent specifically. And so the slope of that tangent would be the instantaneous rate of the reaction at that particular time. And you can essentially ask that for any time that you see on the curve. So that's called the instantaneous rate of reaction. It's at a specific time, whereas the average rate of reaction is at a time interval, so between two times. So you will need to know how to graph reaction progresses if I give you data to do that, and you'll need to know how to calculate the reaction rate, either average or instantaneous, and how to define what the two are. There's a great video tutorial here that goes over a specific example with a specific reaction. It shows you both the reactants and products, how they look on the graph, and also shows you how to use the data to do that. So I highly recommend you watch that, as it will help you with a lot of practice problems that will be coming up. So let's go take a look at our last main concept here. And then after that, in our next video, we're going to do some practice problems to apply the concepts that we just learned. So we saw reaction rates. It's just basically the speed of a reaction, how fast reactants are consumed or products are formed. We can calculate an average reaction rate, and we can calculate an instantaneous reaction rate. And that differs in terms of whether you're talking about a time interval or a specific point in time. Now, you can also compare reaction rates within a reaction using stoichiometric relationships, using the mole coefficients that you've used so many times before this. So if you were going to compare reaction rates, this is our general formula here. You can write a formula to compare the rates of the different substances within the reaction. And why would we do that? Why do we have to approach it that way? Well, when you think about it, that makes sense. Let's look at this situation here. I'm going to just talk you through it first, and then we'll write out a relationship thereafter. But let's look at the production products. We have NO and O2. For every 2 NO formed, only 1 O2 is produced. So what that means is that the NO is produced twice as fast as the O2. So you're getting twice as many in the same time period as you are O2. And that is reflected in our graph. If we go back up here at this graph over here, let's just erase that there. You'll notice that the NO curve is definitely more steep compared to the O2 curve. And that's because we have a rate of 2. This rate is 2 times higher than the rate of O2. And so when we write stoichiometric rate relationships, we like to show how they are related to each other. So for example, O2 is produced at half the rate of NO, and that's based just on the coefficient in the front there. So we can follow the simple rate rule over here to write stoichiometric relationships. And then with that, we could estimate the rate with respect to a specific substance. So I could say, what is the rate of the reaction with respect to NO2? What is the rate of the reaction with respect to the production of NO, or with respect to the production of O2? And this works for either instantaneous or average. It doesn't really matter. You just have to look at what the question's asking, but the process is always the same. So if you want to write rate relationships based on stoichiometry, what we do is for anything that's a reactant, we always start off by putting a negative in the front, because if you don't, then that number will end up being negative because you're consuming it. So you want to put a negative to sort of make it positive in the end. You're doing negative, negative. In other words, you're doing the absolute value. Okay. So I'm going to put negative 1 over whatever the coefficient is, which is 2. And then I'm going to put delta, that means change in concentration of NO2, over delta T, change in time. And that's going to be equal to the same thing here. We'll do 1 over 2, since it's a product, I don't have to put negative, delta concentration of NO over change in time, which is equal to, now here we just have a 1, so we don't really need to put anything, just 1 over 1, which is just 1. So just a change in concentration of O2 over change in time. So essentially what we're saying here is that O2 is produced at half the rate of NO. Or you could say O2 is produced at half the rate that NO2 is consumed at. And also look at this. If we're comparing, let's say, the NO2 and NO, what we're saying here is that the NO and the NO2, since they have the same number in the front here, that half and half, they have the same rate of either consumption or production. So we can say NO is produced at the same rate at which NO2 is consumed, because they have that same number in the front, half and half. All we really did here is we use stoichiometric relationships. So for example, I'm not going to do anything fancy with the formula right now. I'm just going to do something more conceptual for you to think about this. If I say the rate of consumption for NO2 is 4 moles per liter second, and I ask you what is the rate of production for NO, well, you can see it's a 2-to-2 ratio. In other words, 1-to-1. Therefore, the rate of production of NO would be also 4 moles per liter second. Now, if I said based on this 4 moles per liter second of NO2, what is the rate of production of O2? Well, now it's a bit different. We have a 2-to-1 ratio. The O2 is half of the NO2. So what that means is we'd have 2 moles liters seconds. So I didn't use these formulas here yet, but essentially that is what I kind of did in my head. I used that relationship, that rate, stoichiometric rate relationship, to solve a problem like that. So just like we saw with energy, just like you saw with finding moles, you can do a mole ratio with rates. And you kind of already been doing that, but just you weren't really told you've been doing that just yet. So those are the main concepts that you need to be aware of for us to do the practice problems that are coming up. Do review what a reaction rate is, just the speed of the reaction, how fast or slow it goes. Make sure you understand that when we analyze graphs, we take a look at the concentration versus the time. So how does the concentration change over a period of time? And you can look at that whether you're studying the reactants being consumed, because the reactants are used up, or the products being formed, because products are actually formed. Remember, we saw that at the beginning, the reaction rate will be higher than as you go forward, because you just have more reactants to work with. And that just makes sense intuitively. We also saw that you can calculate average reaction rates over a time interval, and that's the slope of the secant, as we mentioned there, between the two times you're interested in. And then we also saw that you could do instantaneous reaction rates, which is at a particular point in time. But in that case, you have to calculate the slope of the tangent. And I do recommend you watch this video tutorial here before you go into our practice problems in the next video, just so you get a better idea as to how to do average and instantaneous reaction rates. Again, here we saw just a sample of how to do the average reaction rate and the instantaneous reaction rate. We were just looking at this from the perspective of a reactant being consumed, and I know that because the curve is going down, so you're using up that substance. If I was looking at a product, then I'd expect to see something more along these lines here, where it's going up on the graph instead. And then lastly, we just saw that you could use stoichiometric relationships to compare rates within a reaction by looking at those molar coefficients that we've seen so many times before. So now we're going to apply that knowledge in a series of practice problems.